My name is Ava Segal, and today I'm going to present an alternative to gamifying rehabilitation that pulls us out from behind our screens using robotic feedback and balance training, and has the potential to provide assessments of balance performance in a home environment. Falling is a common problem in aging adults, where a third of the population falls each year. These falls have serious consequences. If you're older when you fall, you are 2 times as likely to have a serious injury, and you have a 7-fold increased mortality rate. This increased fall risk is linked to a steady decline in balance that's associated with aging, which has been measured by an increasing center of pressure sway velocity. There is some good news, thankfully. Balance control is a learned and adaptive skill that can be retrained, even later in life. Additionally, targeted and demanding training can be effective at reducing falls. So a standard approach to training balance deficiencies involves a series of double limb static and dynamic movements while standing on a board with multi-axial rotation, as you see here. This approach has been shown to improve functional balance in a variety of populations. However, to be effective, it requires a high number of repetitions, which can be boring and lack engagement. Ultimately, this leads to reduced compliance to therapy and lower doses, hindering long-term recovery. So to improve engagement, goal-directed training or exergames provides user feedback, typically presented on a computer screen, that can promote motor learning and shift attention away from the movement outcome. And while this approach has been shown to improve adherence to therapy programs, several barriers to use still exist, including high complexity and cost, as well as a lack of portability. Additionally, excessive screen time can be detrimental to health, causing physical, psychological, and neurological effects. A non-screen feedback approach uses wearable sensors to control a physical robot in a real-world environment. Older subjects who performed an upper extremity task reported that they enjoyed robotic 3D feedback more than feedback on a screen. So we asked the question, can balance performance be assessed with lab-level accuracy using low-cost sensors in a home environment? To answer this question, we designed a gesture-controlled robotic balance training system that uses an IMU-based gesture controller to send wobble board pitch and roll angles wirelessly to a robotic car platform. Then the human must perceive, plan, coordinate, and execute movements to achieve the desired trajectory through musculoskeletal and sensory motor control. This low-cost system is small and can be easily attached to different body segments or training modalities. It also uses a microcomputer for high-level processing and onboard data acquisition. Through this testing paradigm, our vision is to achieve personalized balance training that quantifies recovery progress in a home environment. So the first step to achieve this goal is to validate the onboard IMU signals with established laboratory measurements. Therefore, we conducted biomechanical experiments to assess the potential of the system. Sway was defined as the gesture controller's IMU pitch and roll angles, and this was compared to 2 gold standard motion capture measurements, the wobble board angle and center of pressure position. Sway velocity was calculated as the first order finite difference of sway, and finally, Pearson correlation coefficients were calculated for each signal pair across conditions. The following representative plots are of pitch and roll sway trajectories that have been normalized to the peak rectified signal along the y-axis and across a 10-second time frame along the x-axis. The overall results demonstrated strong correlation between the signal pairs across all comparisons. Similar plots of sway velocity show a strong correlation as well, although less strong and twice as variable as sway, and this is likely due to noise with signal differentiation. These results demonstrate the potential for tracking remote training progress using low-cost gesture controller sensors. This could reduce therapy time and cost, as well as promote long-term adherence and the efficacy of at-home training programs. Our next steps are to conduct a full validation study across age groups. We also plan to compare robotic and screen-based feedback by studying the biomechanical strategies, motor learning, and engagement of younger and older adults. At this time, I'd like to acknowledge my funding source as well as my co-authors, and I'd be happy to take any questions. Feel free to email me, and thank you so much for listening.